Okay, any questions about the inertial reference frame, Newton's first law? Well, you see, a person is not an inertial reference frame. But you can, for example, choose the origin of your reference frame to be a point on you. I can just say that, okay, there is a point, this point is the origin of my reference frame, this is the x-axis, this is the y-axis, and this will be the z-axis. That you can do. That's the reference frame. The next question is whether it is an inertial reference frame or not. It depends on, are you moving or not? For example, Earth, we will assume that it's an inertial reference frame. If you move at constant velocity relative to Earth, then it's an inertial reference frame. Then you are an inertial reference frame. If you are not moving at constant velocity, then you are not an inertial reference frame. Or another way to look at it is, for example, what's your name? Arif. Okay, Arif is sitting over there. I choose the origin of my inertial reference frame to be a point on me. It's moving with me. I look at Arif. There is no net force acting on him. The net force is zero. He's at rest and he stays at rest. So this reference frame is an inertial reference frame. But if I just decide that I just want to go this way and back and that way and back, still there's no net force acting on him. But he started to move back and forth relative to this reference frame fixed on me. So now, although there's an object without any net force acting on it, I can just imagine isolating him. He's accelerating. He's changing the state of his motion. His velocity is no longer constant, although he's isolated. So the reference frame that's moving with me is not an inertial reference frame in that case. It's not, being an inertial reference frame is not a definition that you can just pick an arbitrary reference frame and say that it's an inertial reference frame. If you want to test whether a given reference frame is inertial or not, you have to use the Newton's first law. Locate an isolated object. Does its velocity change? If its velocity is changing, then you are not an inertial reference frame. If the velocity is not changing, then that reference frame is an inertial reference frame. You see, for example, the coordinate axis, we were just arbitrary in choosing them. We could choose one coordinate axis like this, the other one like this, or one is pointing over here, the other one is pointing over here. It's just our choice. But we cannot choose which reference frame is an inertial reference frame and which is not. This is how we define how we test whether an inertial reference frame is, whether a reference frame is inertial or not. Okay, now Newton's second law. Yes. No.
It appears as if Newton is only explaining what should be. That's what I think. He's explaining what should be. But how was he able to explain what should be from what is?
Now, what he does is, okay, the first law is not really what should be. It's what he observes.
Well, because no object moves at a constant velocity. No object.
Yeah, that's true. That's an idealization.
So how was he able to tell what should be from what is?
Well, okay, your friend has a point. You see, if you go back to the Newton's time, what does he know? If you throw an object, it eventually stops. In fact, before Newton, people believed that it was just the natural state of the motion. Everybody tends to stop. There were all these theories that, for example, the universe was just, the Earth was the center of the universe. Well, that is also a natural consequence of what the people observe, because what they observe is all the solid bodies fall down. That's the observation. So whatever is solid in the universe, they should just fall towards the center. So the Earth is nothing but the center of the universe, known universe. That was what was known. Now, of course, Newton just didn't come up with, the story of the apple falling on Newton and coming up with a theory of gravity is just not true. The same thing holds for here. It's just he made years and years of observation. As your friend points out, nothing is moving at constant velocity. Well, it's not exactly true. For example, in the reference frame fixed on my body, this is moving with constant velocity. It has zero velocity, but that is a constant velocity. So he knows at least one part of this state, that if something is at rest, if there is no force acting on it, it should be at rest. Now, what about if something is moving at constant velocity? There is nothing that moves at constant velocity in real life. Everybody's velocity will be fluctuating. But nevertheless, just taking this step from what he observes approximately and what is the basic underlying principle, underlying philosophy, that is what we call the genius.
Well, I'm not doubting the fact that maybe he was a genius, because I believe in probably in physics, in chemistry, or in any part of science. Some of the theories or laws might not be true, but when everybody accepts it, we accept it as true. Some of the theories are like that. People accept it, but if you go deep, for example, when Einstein was observing Newtonian mechanics or whatever, and so many people accept that this is true, but in actual sense, in reality, it might not be true. For example, the two examples that maybe explain Newton's first law, that is when a bus is moving, you're in the bus and suddenly the driver presses brake and you move forward. If you look at that situation, the bus itself is not moving at constant velocity, so the bus is accelerating.
True.
At that point, and then you're also accelerating. So if you look at that...
Okay, first of all, the bus is accelerating. Well, let's just put everything precisely. The bus is accelerating relative to Earth.
Yes.
Okay. The bus is not accelerating relative to itself. Okay, now you can continue.
Okay, so let's assume the bus is accelerating relative to Earth, and you're also accelerating because you're in the bus.
True.
So now, when the driver pushes the brake, you move...
you are again accelerating.
You move forward. That's the observation at that point. You move forward. But if
True.
you look at that, we can only observe, draw conclusions from the accelerations of you and the bus at that point where the brake was pressed. We can only draw conclusions from the relationship between the acceleration of the bus and your acceleration relative to the Earth at that point. So I don't know how the velocity comes into that. So I think we should be talking about the relativity of your acceleration and the acceleration of the bus at that point when the brake was pushed. So I don't know why it was explaining it in terms. I think it should be explained in that direction, using the relativity of the acceleration of you and the relativity of the acceleration of the bus relative to the Earth at that point. So why was he using the velocity? Because sometimes I believe that if people cannot disprove your equation, they accept it as true. But your equation might be wrong.
Well, how does the physics work? That's a question mainly related about this thing. Okay, one of the things, let's say in quote, shortcomings, you make only a finite number of observations. Is this law correct? You just choose a reference frame, let's say an inertial reference frame. Is this law correct? You make, let's say, 100 measurements, 1,000 measurements, 1 billion measurements. But you only know that this law is correct for that 1 billion measurements, not for the next billion. You can never be sure. The same thing, let's take the example of general relativity, not gravity. If you just drop an object, we know that it will fall. How many objects did we test this for? Let's say 1 billion. The next one, we cannot never be sure that it will fall. We didn't test it for that. But nevertheless, if you would bet, I would bet that it would fall down. Now, the law is not a good word, let's say, although we are still using the word law. Newton's laws are valid. We still know that the Newton's laws are correct description of world, even today. But we also know that under which circumstances we cannot use Newton's law. It's not the laws that are applicable in every case, but in quite a large number of cases we can use Newton's laws, and they have survived the tests of time. We made experiments, we made many experiments. Even every day we are actually making experiments, and we haven't observed anything that contradicts Newton's laws as long as we stay within a limited range of physical phenomena.
So basically what you are trying to say is that until we find something that contradicts it, we remain valid.
True. And Newton's law will still be valid. For example, I test this one falling down. For this object, Newton's law will still be valid, even if there is a phenomena that contradicts Newton's laws. Then the question will be for the improved theory. The improved theory should also explain me why are the Newton's law valid in this case. For example, now we know that we have the special theory of relativity, which tells us that the Newton's laws are not so correct. If you are talking about a reference frame that move at large speeds relative to each other, then the Newton's laws are not correct anymore. But the special theory of relativity also tells me that why Newton's laws were believed to be correct beforehand, because we never experimented with objects moving very fast. So as long as the objects are moving at small speeds relative to each other, at small velocities relative to each other, special theory tells us that the Newton's laws should be valid. So if Newton's laws are wrong, completely wrong, then special theory of relativity should also be wrong, because it tells us that Newton's laws are valid within the range of applicability. Special theory tells us that we cannot use Newton's laws in every case. But if the relative velocities we are talking about are small, we can use the Newton's laws and they should be correct. The same holds for quantum mechanics. Quantum mechanics tells us that the Newton's laws should be correct, should be valid in certain systems, not valid beyond that. But all the theories we have, now we started with the Newton's laws, then we had the special theory of relativity, now we have a theory that is valid more generally, which contains Newton's laws. Then we had the quantum mechanics, we even enlarge it further. So we now have an even larger theory which contains Newton's laws. And then we have the general theory of relativity. Now our understanding of nature is applicable even to a broader possible cases. And general relativity still agrees with Newton's laws within a certain range. So all these new theories are telling us that Newton's laws are correct. And most probably, if we eventually get even a better theory, it will tell us that general relativity is correct, quantum mechanics is correct, etc. All of them are correct within the range that they are applicable. They will tell us the limits, but as long as we are within that limits, all of these theories will be correct. Now, the Newton's first law, we can also write it in terms of acceleration. It just tells us that the acceleration is zero if the net force is zero.
Professor, just we are saying the net force is zero. And in the Earth, we are thinking this. How it is possible? Just a little bit. Because of gravity, other factors are thinking. Another thing, you are astronaut, you are moving inside a spaceship and then going to somewhere. But not close to any star, galaxy, you are in gaps. And you are going inside the ship. That's me. It's explaining first law, basically. But the second thing, in the Earth.
Okay, if you want to talk about the second law, let's first write the second law. Okay, let me just first write the second law, explain what the second law tells us about, and if you have questions, we will discuss that. Well, this law can be written as, well, of course, just keep in mind first that this law is valid as long as the first law is valid. So this is only valid in an inertial reference frame. The first law just kind of sets the stage under which the second and the third laws should be valid. Okay, this is basically the statement of the third law. That is the acceleration of an object. Okay, the acceleration we had already defined. So we can measure, we know what acceleration is, we can measure acceleration of an object is proportional to the force. Okay, now the first question, what is force? We didn't define the force yet. Acting on it and inversely proportional to its mass. Now we also didn't define its mass. What is mass? So if we want to make full sense of this law, we have to define what force is and what the mass of an object is. Now, from this law, you can say that the force is anything, any effect, any phenomena that causes acceleration. That is what we call the force. Now, this law we can also write mathematically in this way. F over m, or F is equal to m times a. So force is anything that causes acceleration. And we can measure the force by measuring the acceleration of the object, multiplying it with the mass of the object. So this second law is all, in fact, the definition of the force in a sense. What are possible forces that we see in nature? Well, that is a question that we are still looking for. Can we write some general laws about the forces that objects will feel? That is, if I say that 80% of fundamental physics research is about identifying forces, it won't be far from the truth. Now, we already know some general forces. We will be discussing forces one by one, some of the general forces that we see quite commonly. But before that, let us go back to the mass. What is mass? Okay, the second law tells us that the objects have this property called the mass. How do we define it? How do we measure it? Now, to measure it or to define it more properly, we also need Newton's third law. Which basically means that if A exerts a force on B, let's call it this FA, then B exerts a force FB on A, and FA is equal to minus FB. These are sometimes called the action-reaction pairs. Okay, don't get confused. It's not one of them. The FA is the action, FB is the reaction force. No, don't separate these two. It's a common. Both of them are just pairs. They are either both of them exist or both of them do not exist. So you cannot really separate them. Both of these two are action-reaction pairs. Now, one thing this also tells us that for every force that you feel, there's some other object that exerts that force. You cannot just have a force without having a source. Now, how will this help us to determine the mass of an object? Now, let's take two masses. Large M and some small m, let's call ms. This is what we call the standard mass. Now, if you remember the first week, we said that certain things are defined. Like, we define the unit 1 second to be with using some special light emitted by an atom. We define 1 meter using the speed of light. So those things are defined in terms of fundamental properties of matter. But unfortunately, we don't have such a fundamental property of matter for mass, fundamental definition. We take the standard mass, the generally used 1 kilogram is somewhere in Paris. So you just measure mass of any object relative to that 1 kilogram in Paris. So how do you determine the mass, or how do you determine the ratio of the masses? Okay, one thing you can imagine is take one mass. This is our unknown mass m. Then we have the standard mass. Let them exert forces on each other. For example, you can just imagine attaching a spring. They exert forces on each other. Well, Newton's third law tells me that the force that m, large mass m, feels is equal to minus the force that the standard mass feels. So these two should be the action-reaction pairs. Well, if two vectors are equal, then their directions are equal and their magnitude should also be equal. So the magnitude of Fm is equal to magnitude that the standard of the force that the standard mass feels. But the magnitude of the unknown mass m feels, the magnitude of the force is nothing but, according to the second law, its mass, unknown mass, times its acceleration. This should be equal to the mass of the standard mass times its acceleration. But this tells me that the unknown mass should be equal to the standard mass times the ratio of their accelerations. Okay, one thing, don't get confused. There's no minus sign over here. Because this is a vectorial equation, so this minus sign tells me that they are two vectors having the same magnitude. This is this equation. They have the same magnitude. They're just pointing in opposite directions. So this is the equation for the magnitudes. So if you look at this expression, well, we know how to measure the acceleration of objects. Once we determine the acceleration of the standard mass and the acceleration of our unknown mass, then we know the standard mass. We just define it to be 1 kilogram. And then the unknown mass is nothing but this standard mass times the ratio of the acceleration. This is how we define the mass of any object. And if we go back to this one, so we can determine the mass by this simple setup. Once we measure the mass, if we want to find the force acting on an object, we just take its mass, multiply it by its acceleration, and then that product tells us what the force acting on the object is. What is force? Well, force is anything that creates acceleration. What is that? We don't know. We have another explanation for the force, but I will just go over it in a moment after your questions.
Back when you wrote that Fa equals to negative Fp, while I understand that obviously Fa is the opposite of Fp, hence the negative sign, is there a need to put the negative sign, since doesn't the subtext B clarify that these two are not exactly the same? Fa is not Fp, right? Hence the small text B.
Okay, Fa is not 2Fp, Fa is not 3Fp, Fa is minus Fp.
Alright, so is there a need to write minus, or did you do it just to clarify for us?
Now, this is the correct mathematical expression. You see, I have these two vectors. I know that these two vectors, they are in opposite direction. They have the same magnitude, they are in opposite direction. If you multiply a vector with a minus 1, take Fp, multiply it with minus 1. You get a vector that has the same magnitude as Fp, but pointing in the opposite direction. But the vector that has the same magnitude as Fp and pointing in the opposite direction is Fa. So this minus sign has to be there.
What is the starting mass? Because I know usually when we attend labs, we measure the mass of objects, and probably we place an object on the scale and give you 1 kilogram. So there must be standing mass, which is internationally recognized. So what is the standing mass?
Well, people are just, one day, they just came together and decided to call an object of this size, made with certain metal, 1 kilogram. That's just convention. That's just a definition. Now, of course, the problem is when you measure the mass of objects, you don't go to Paris and compare it with that mass. So what is done in real life is every country has their own standard mass. They should have their standard mass. So they just go to Paris, they compare it with the mass, standard mass in Paris, and they determine that it has exactly the same mass. They measure the acceleration, let's say, and then they show that the acceleration has the same magnitude, and hence the mass should be the same. So they bring it to here. So if you want to have and every country should have some calibration institutes where, for example, you want to make a precise experiment and you have to determine the mass precisely. So what you do is you take your instrument, go to that lab, go to that calibration lab, and make sure that your measuring device measures 1 kilogram for that mass. That's how you calibrate it. And then you bring it back to your lab and you measure the mass. Well, most of the time what you use to measure labs is their mass in just ordinary labs, not in precise measurements. But you go to, for example, you go to shop or Migros supermarket, you just put it on a scale. The scale doesn't measure the mass. Although you read just kilograms, it's not actually measuring the mass.
My other question is, when you have two, because you have explained the third law, so I can bring it. When you have two objects
Okay.
collide, at the point of collision, let's assume probably that's an elastic collision. Let's assume it's an elastic collision. At the point of collision, probably the time.
Well, if you want to discuss about the collisions, I would rather wait until we discuss the collisions in class. After that, we can discuss the collisions. The breaking the stone with bare hands. Okay, that wait until we discuss the elasticity. Now, currently we are just looking at simple systems, like point objects. You cannot divide points, or expanded objects, but they are not changing their orientation or they are not breaking up. So let's stick with such simple systems for the time being. Once we settle down with the concepts, we all agree what we understand about these concepts, then we will be moving on to more complicated problems. Other questions? Okay, so I will just open up parentheses to present our modern understanding of forces. Question? No, this is not a question. I will explain. I'm sure you have already heard that if you have two charges, the relative force between the two, this is electric force, is proportional to 1 over r squared. Another thing that you have we didn't discuss this yet in the class, but I'm sure you have all heard about that. The gravitational force between two masses is also proportional to 1 over r squared. Why both of them are r squared? Have you ever thought of that? These are two completely independent forces as far as we know. Maybe one day we will discover that they are related somehow, but at least currently to us it seems that they are completely independent forces. Why do they behave identically with the separation? Now we have an explanation for this one, because nowadays, when we say force, at least Newton defined it as something that causes acceleration. in the modern particle physics understanding, there is actually not a real force, in the sense that what is actually happening is we are just exchanging particles. Like, let's say, he is one charge, a positive charge, I am a positive charge. So we will be feeling an electric force, we will be exerting an electric force on each other. So what is actually happening is, for example, as an electrically charged object, I constantly emit light, photons. Well, these are weird photons in the sense that although I am constantly emitting photons, I'm not losing energy. They are, as I said, they are weird photons. He is also constantly emitting and absorbing photons, just like me. I am emitting photons, absorbing photons. He is emitting photons, absorbing photons constantly. Now, when we come close together, what happens is I emit a photon and he absorbs it. So if he absorbs it, then my energy will be changing. His energy will be changing. This photon will carry energy from me to him. And there will be also this so-called momentum transfer. Our velocities will also change due to this transfer of energy, let's say. We will be transferring energy. Since we are exchanging energy, our velocities will be changing. But changing velocity means there is an acceleration. But if there is an acceleration, Newton defines it as force. Now, how is it related with this 1 over r squared? As we are exchanging photons, I emit photons in every direction. And he can absorb only the photon that moves in his direction. Now, the same thing holds for him. He constantly emits photons, and if some of those photons comes into my direction, I will be absorbing them, and hence we will be exchanging photons, and we will be exchanging energy and velocity, which will create the force. But since we are both emitting photons in every direction, the density of the photons that reaches me from him, you see, all the photons will be distributed more or less uniformly on the surface of a sphere. He emitted them, they are moving in all directions, so they will be just moving on the surface of a sphere. The sphere will be just getting larger and larger. So if he is here, he is emitting photons, let's say one is moving, they are moving in all directions. If I look at all the photons that he is emitting at the same time and their position at a later time, at some time they will be here, at the next time they will be here, so they will be just moving outward. But since the photons are being distributed on the surface of the sphere, their density, their number is constant, but the number will be just, which is constant, it is the surface density times the area of the sphere. Okay, what is the area of the sphere? 4 pi r squared. So the density of photons that comes in my direction from him is proportional to 1 over r squared. So since the density is proportional to 1 over r squared, the number of photons that I can absorb from him also moves as 1 over r squared. So that's why the force that we exert on each other, the electric force that we exert on each other, is 1 over r squared. The same thing holds for gravity. The gravity is also, we believe that it is caused by an exchange of particles that we call gravitons. And the same principle applies there. So that's why both the gravitational force and the electric force, they are both 1 over r squared. Although they are completely different forces, the underlying nature, the behavior of the nature, let's say, since it's the same, meaning that we are in 3 dimensions and the area of a sphere in 3 dimensions grows as r squared, the force or the change in the velocity, the energy exchange per unit time, let's say, behaves as 1 over r squared, and Newton calls that exchange in velocity as the force. Okay, if that didn't make any sense, you can just forget about it, but just keep in mind. Yes?
Yeah, I want you to go back to why density inversely proportional to R. I want you to.
Density is proportional to 1 over r squared. Because the number of photons doesn't change. And the number of photons on this surface is equal to the surface density, that is the number of photons per area, times the area. So this should be constant. So the density has to be 1 over r squared. The total number is constant, it doesn't change. Now, any question? Yes? Well, the force, we interpret the force as exchange of some particles, some other particles. Like for electric force, photons, just like the light is made up of photons. For the gravitational force, we believe that there are gravitons that the exchange of gravitons causes this force. Well, we don't know yet. We didn't measure gravitons. We couldn't observe them. We couldn't even write the theory of gravitons yet. But nevertheless, we believe that the gravitons exist. It's just a belief for the time being. We have two other fundamental forces, and we believe that there are also some other kind of particles exchange. And we observe. We observe the force carriers for weak force and for the strong nuclear forces. Well, you see, our current understanding of how nature works is that how these forces, let's say, work is that particles exchange other particles. For example, charged particles exchange photons. And by exchanging photons, they transfer energy and they change their velocity. But Newton defines the force as anything that causes acceleration. So this exchange of particle causes acceleration. But that is what Newton calls the force.
So are you saying the density probably should be, let's assume the number of photons
are being created? True. True. Yeah, the photons are only created at charges, electric charges, and not in empty vacuum. Other questions?
Is there a modern understanding for the
Definition
definition of momentum?
of momentum. Well, you see, the modern understanding is that momentum is a more fundamental object than velocity. Now, you see, we will be defining momentum. Now, let's discuss it when we define the momentum more precisely. Now, you are probably used to defining the momentum in terms of the velocity and the mass. But in the modern science, we almost always work with momentum. And then using momentum, we talk about the velocity. Well, you see, we don't. At that level, we still call it force, but we are not going to, we are not just looking at the we don't go inside the protons and measure the forces, measure their accelerations, etc. But we know that at least we can compare Newton's laws, Newton's observations, with, let's say, the electrostatic force. We know that electrostatic force in the modern understanding is just exchange of particles, which causes a change in velocity and hence acceleration, which Newton calls the force. The weak force, we know that it does the same thing. There are exchange particles over there. So if we could measure the velocities of each one of the particles feeling this weak force, we believe that we should measure some acceleration, and hence it would correspond to what Newton calls force. But we are not directly comparing weak force with the Newton's laws. We cannot measure the weak force in the sense of Newton. We have other means of measuring it. Now, what are the forces that you are experiencing? What are the forces that you are experiencing in your everyday life? Gravity. Okay, let's just get rid of gravity first. Okay. Resistance. Well, you see, resistance is not something that we call a fundamental force. Resistance is electromagnetic force. I will come to that. What other forces? Okay, how do you feel the nuclear force in your everyday life? Okay, you push the table. Okay, resistance. It's involved in resistance. It's kind of a friction. Push, pull. Some push, other pull. They are all electromagnetic forces. The force that helps you to sit on your chair and not pass through your chair, although there is gravity, is electromagnetic force. That is also resistance. Okay, these are basically the general groups of forces that you can imagine. So your chair is pushing you upward so that you can sit on the chair. Gravity is pulling you down. The chair is pushing up. Now, how is it the electromagnetic force? You see, what you are made of? You are made of atoms. When you hold this pen, or this thing, let's say when you are holding this gyroscope, what's actually happening is you have your fingers. They are made up of atoms. This thing is made up of atoms. Atoms are made up of nuclei which are positively charged and electrons going around the nuclei which are negatively charged. So what's happening here is when you bring your finger close to this thing, this metal part, the atoms of this metal part and the atoms of your finger, they are getting very close to each other. But when they get very close to each other, electrons get even closer than the nuclei. So electrons start to push each other away. So, and after, if they come sufficiently close, you cannot push your fingers any further. So it's still the electrostatic repulsion between the electrons in your hand and in this metal that creates this push-pull. The resistance is also basically when you move an object in air, when you drop this piece of paper in air, there is an air drag force exerted on this, but the main reason for the drag force is that the atoms making the air, they collide with the atoms making this paper. And collision is nothing but the electrons coming very close to each other. When they come very close to each other, their electrons will repel each other. Well, there are also all these attractions between electrons and nuclei, and the repulsion between the nuclei and nuclei, but what wins will be the repulsion between the two if they come very close to each other, and hence they just bounce back. So all the forces in your everyday life that you feel, they are actually electromagnetic forces except then gravity.
So in any normal day circumstance, is it possible for two nuclei to touch?
For two nuclei? No.
No, right? So is it wrong to say that we're essentially always floating?
What do you mean by touching?
You can't ever touch anything. The electrons that are...
I mean, the distance between two objects in the microscopic world, they can be zero. For example, neutrinos are just passing through you. But two electrons, they will never touch. Two nuclei will never come that close to each other. Any other questions? Okay, before you go, I will be sometimes just telling you what the homework questions will be in advance. But the homework gets official only when it's uploaded in the OTT class. Okay, so whenever I say that something is a homework, I will prepare it, put it in OTT class, and you will see it in OTT class. You already have one homework for next Tuesday. You will probably get one today, another one today or tomorrow for the following week. On Tuesday, I want you to bring your homework at the beginning of the class. Don't bring it at the end. I will not allow that.